So screen is also visible, so we can start. So I'll give like I can see some new faces so who were not there in the previous class. So I will just introduce myself, a brief introduction I'll give, and then we can start with the problem. And hope you would have seen the previous week's lecture that I have recorded and I put in my YouTube channel. Hope you are able to access those links which you are sharing with the NPTEL team. And if you have any issues in accessing those videos or links and all, you can put in the message. Then I'll take care of it. Okay. So I'm Akhil. I'm a PhD scholar from IIT Delhi. I'm currently in my fourth year of my PhD. So I'm working under the supervision of Professor Dhanya Sethi, and my research area is groundwater modeling. And I did my bachelor's from NIT Calicut. It is in civil engineering, and after that I was graduated in the year 2018, and then I worked for 2 years and then joined for MTech in IIT Guwahati, where I worked under Professor Srija Pekat, who is a course instructor for this particular NPTEL course. And now currently I'm enrolled in IIT Delhi from the year 2022. So in the previous lecture, what we had seen is we started off with the previous week lectures. We started off with the what is hydrology, the definition of hydrology, and what are the different compound. Then we move on to from hydrology to the hydrological cycle, and what are the different components of the hydrological cycle, and what are the different processes of the hydrological cycle, and then we understood that there is a need to quantify this or model these different hydrological processes. To model these hydrological processes, we will be making use of the well-known laws of well-known, well-defined laws, which are the law conservation of mass, momentum, and energy. So these laws, but the drawback is that they are defined in the Lagrangian frame of reference, where we will be tracking the particle, how a particle moves. But if when we are dealing with fluid, the issue is uh, just a minute. Okay. When we are dealing with fluids, the issue is it is difficult to work with the what we say the Lagrangian frame of reference, because we are using another frame of reference there, that is called the Eulerian frame of reference or the control volume frame of reference. So to so there is a gap, like the equations are defined in the Lagrangian frame of reference, and then we have to move on to the Eulerian frame of reference. So that gap is being filled by the help of the theorem called the Reynolds transport theorem. So we also saw the definition, that is the derivation of the Reynolds transport theorem. What are the different components in the LHS and RHS? That are all we saw in the previous class. And also we saw the concept of residence time, and also the concepts of water budget equations. So in this particular lecture, in this particular just yeah yes, now am I audible? Hello, 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 am I audible now? Okay, 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 sorry. Just a minute. Huh. So that particular gap was filled by RTT, and we also saw the concept of uh, the residence time and also the concepts of the water budget equations. So in this particular lecture, problem solving section, that is for the second week, if you had seen the lectures, it is about the atmospheric water. So we saw the different phases or different components of the water cycle, right? And in the previous problem solving section, we also dealt with the residence time of an water particle in the atmosphere. So we saw that compared to the oceans or groundwater, it is very less, and it is coming around like 8.2 something days or something. And we also understood that that is why the weather forecasting and all that we like the rainfall forecasting and all, it happens for 7 days. So because that is the maximum time we can track those particles like in the atmosphere, like water vapors. So in this particular week, the lectures were dominantly on based on the atmospheric water vapor, how we can, so each of the component in the previous lecture we saw there's a need to model those. So in this particular section week, we were trying to see how to model the atmosphere, how to track the atmospheric water vapor using the laws of motion, that is the conservation laws that we are having, and using the well-known theorem, that is the RTT theorem that we have, we already know from the previous lecture. Okay, so I think we can directly move on to the first question. So that is, so in the previous lecture itself I have said like what the format I will be following is, I'll be starting, uh, I have selected these questions which will be covering the entire the all the important concept of the entire lecture, entire lecture taken in the previous week. So and I have selected these questions in that way, all the, so that it will be like a recap for you. So the first question is related to the your lecture 9, that is the Reynolds transport theorem for atmosphere. So you can have a read on this question. So in the RTT, in the Reynolds transport theorem applied when applied to the atmospheric water vapor. So now we already defined the or derived the RTT. Now we are going to apply to different components, okay, to model them. So we are applying to the water vapor. So the so the LHS term, that is m dot v, uh, accounts for the phase changes for the for a control volume where condensation is dominant. The sign of mv is, so I think you have read the question. So we will come to the options. So before that, we let's see how RTT is defined for the atmosphere. Okay, so you already know what is how we can write a RTT equation. So that is RTT we already derived in the previous class. RTT, as in the LHS we have dB by dt, that is the rate of change of the extensive property, that is equal to d by dt, that is rate of change of across the triple integral, that is volume integral of beta rho dv plus across the control section beta rho v dot dA. So this is dot product. So we already saw this in the previous lecture. So it has the rate of change of extensive property is given by the rate of change of this is also rate of change of the extensive property across the control volume plus the rate of change of here then the second term, there is not rate of change, it is extensive property, the next extensive property from the that is moving across the control surface, that is from in outlet minus inlet. So this is the RTT formula, and now we are going to apply this particular formula to our atmosphere or atmospheric water. So here first thing we need to do is to define our intensive is to define our extensive property, right? So extensive property, here we are defining it as the mass of moisture or water vapor. So basically we need to track the water vapor, right? The water in the oceans or any water body are getting evaporated, and we need to track this. So the extensive property will be the amount or the mass of the moisture or water vapor. And also, if we have seen the lecture, ma'am has made it clear there are two things. One is moisture. You need to know the difference of these two. One is moisture and one is moist air. both are not same. Moisture is nothing but the water vapor in the atmosphere. So we are interested in tracking this using RTT. And the second one is moist air is water vapor or moisture plus the other gases. So in the atmosphere there is not only moisture, there are different gases, right? There are different types of gases which are there in the atmosphere. So that that combination is called the moist air, and in the moist air the water vapor alone is called the moisture. So this difference, it should be clear. Moisture is nothing but water vapor, and moist air is the moisture plus the other gases that is present in the atmosphere. So from this, one more thing is clear, that is moist air is the flowing fluid, right? So we have defined this RTT, this particular RTT we had defined it for some flowing fluid, right? So what the flowing fluid, there is a flowing fluid within the control volume. If you remember correctly, we had derived this by considering a control volume, right? So inside this control volume there is a fluid with a density rho. So here in the case of atmosphere, the flowing fluid is nothing but moist air. So flowing fluid is moist air, but the B, that is the capital B, that is extensive property, is the mass of moisture, that is not the mass of moist air. So when we take beta, beta is the intensive property, right? Intensive property will be dB by dm. So this relation we already know. So here B is mass of moisture, but m is the mass of moist air. Or in this particular relation, in this particular formula, the denominator mass represent the mass of the flowing fluid. So in earlier case, in the previous lectures where we took B as mass, then dB by dm was becoming 1. Here the dB by dm, beta is not equal to 1. It is because the denominator, the change denominator is nothing but is not equal to the numerator. The numerator is the mass of the mass of the moisture or the water vapor, and the denominator is the mass of the flowing fluid. Okay, so this will not be equal to 1. So this is why it is important to understand the difference of moist air and moisture. And also we need to understand, in our RTT we are always dealing with the flowing fluid. In atmosphere, the flowing fluid is moist air, that is water vapor is there, and the other fluids are also there, and other gases are also there. Okay, so this particular term dB by dt is not equal to 1, and we call this as, if you see in the lecture you would be knowing, it is we are calling this as specific humidity, right? And we represent them using the notation QV. Okay, and just a minute. So in the RTT, so this particular term is, you are clear now, that is dB by dt is clear. Okay, so not dB by dt, I'm sorry. So we are clear with beta is clear now. So next thing what we need to understand is, what is this dB by dt. So beta we already got, beta is not equal to 1, it is equal to QV. The next thing we have to find is, what is the LHS, that is dB by dt. And this question is also talking about the LHS term, right? So the LHS will be, that is dB by dt usually if B is mass, dP by dt should be equal to 0, right? Because mass is, because of by conservation of mass, right? The we can neither be, the mass can neither be created nor be destroyed, so it should be equal to 0. But in case of atmosphere, uh, what is happening is there are two processes happening, that is, one is condensation, the other is evaporation. So the water from the water bodies gets evaporated and becomes in the vapor form, and when they rise up and the temperature decreases, they cool down, and when the cool down, the condensation process take place, and it gets converted into liquid. So these are the two processes that have happening in the atmosphere. So here when you see, the water is the moisture, or the moisture is getting converted, or the water vapor is getting converted into two states, that is, from liquid state to liquid phase to gaseous phase, and from gaseous phase to liquid phase, right? So there is a change in phase happening. So, and also you are clear that you know that the mass can neither be created nor be destroyed, but it can be changed to one form to another. So that's why dB by dt is not representing whether the mass is changing with time. Here it is representing whether the how rate of phase change, how the phases are changing. That's why in the question also you can see the LHS term, this particular term accounts for the phase change. It is not that the mass is changing with time. The phases are changing. That phase change is being accounted by the LHS term. Okay, so this we are calling it as a phase change, and we are representing it by a term m dot v. And in the question, they are asking about this particular LHS term, and they are asking us to consider a control volume, and when condensation is dominant. So I already told you, if you are when you are trying to model a atmosphere, we take a control volume in the atmosphere and we apply this RTT, right? So in when we apply this RTT, we are trying to understand what is this dB by dt. So dB by dt accounts for the phase change, and dB by dt accounts for the phase change, and this particular dB by dt, that is equal to m dot v, can be positive, can be negative, and can also be equal to 0. So we need to see when this will be positive, when this will be negative, and when this will be equal to 0, right? So this particular m dot v, that is rate of change in moisture, will be positive when evaporation takes place. So the reason is obvious, because this is actually the rate of change of B. B is nothing but moisture, right? If evaporation takes place, more vapors will come, right? More water will be converted to vapor. So in a way, when evaporation takes place, uh, so the amount of the mass of this is getting increased. So that's why dB by dt will be positive for evaporation, and dB by dt will be negative for condensation, right? So dB by dt will be negative condensation. That is because condensation is the process in which the vapors are getting reduced. The vapors, they get condenses and forms clouds, and it rains. So there the mass of vapor is reducing. So it will be negative when it is condensation happens, and it will be 0 when both these processes are not taking place, right? So that will be 0 when the moisture remains the same. So if you consider a case, the evaporation took place, and the water get evaporated at the same rate, the condensation is also happening, right? So the net change in the moisture is 0. Evaporation is happening at the same rate, condensation is also happening, right? So whatever the vapor gets are created by evaporation are getting destroyed by condensation. So in that case, the rate will be equal to 0 when evaporation and condensation are in equilibrium, equal to condensation, both are in equilibrium. So these are the three cases to which in which we can understand dB by dt. So in this question, they have mentioned that the condensation is the dominant process. So that means condensation exceeds evaporation. That is, more moisture will be getting destroyed, or the mass of the moisture with time will be reduced. So dB by dt will be negative, right? So it won't be positive. It will be positive. It will be positive when evaporation dominates condensation. It will be zero when evaporation and condensation are in equilibrium. That is, net change in mass of the moisture is constant, and it depends on the temperature gradient. That is, it is wrong, right? Does not depend on temperature gradient. So the answer is negative. So when condensation dominates, the uh, this will be negative. So this is the answer. So through this question, our main intention was to make how to make the terms within the RTT clear for an atmosphere, right? So what we need to understand is that it is not equal to zero. That is, here the mass is constant, but it changes phase from one phase to another. Total mass will be conserved, but it can change phase from one phase to the other phase. Okay. So I hope the first question is clear. So let's move on to the second question. So this question is basically to get an idea of the terminologies which we are going to use in this particular problem solving section. So these terminologies are basic terminologies for when we relate to atmosphere, right? So the question is, which of the following statements defines relative humidity? So I am sure, like in this particular in the previous lecture, you have been introduced with different terms, like what is we already saw one term, that is specific humidity. We also saw terms like what we is being asked in this question, that is relative humidity, and also terminologies like vapor pressure, also like dew point temperature. So this is just to get a recap of all these terminologies. This particular question is just to get a recap of all these terminologies, so that this will be helpful when we are going to the numerical type questions. Okay, so we can start with the very first thing, that is the specific humidity that we already saw. So one particular definition which we saw was specific humidity is dB by dm. That is the rate of that is the mass of moist air by the change in mass of moist air by change in mass of the change in mass of moisture by change in mass of moist air. That is one definition we saw. This is the one particular definition of specific humidity, right? The change in mass of moisture divided by the change in mass of moist air, right? So the so another definition, so that definition we can write QV, we can write it as is the density of water vapor. So if we are taking same volume, then we can write in this way, right? Density of water vapor by density of moist air, that is rho V by rho A. So this is what specific humidity is. That is density of moist air, or mass of water vapor, mass of moist what density of water vapor, or density or mass of water vapor, or mass of moisture divided by density of moist air, or mass of moist air. That is nothing but mass of moisture plus the other gases. So this is so if we see the options, the ratio of mass of water vapor to the total mass of moist air. So the first option is nothing but specific humidity, right? So it is not relative humidity. The first option is nothing but specific humidity. The specific humidity is nothing but mass of moisture by mass of total moist air. Okay, that is clear. And also the specific humidity, we can say it is a moisture in overall volume of moist air or in the mixture of gas. So like we can generally say specific humidity is nothing but how much moisture is there in the atmosphere. That is also a definition for specific humidity. That is, in the atmosphere by default it is clear that there are moisture and also other gases. In that, how much is the ratio or the percentage of moisture or water vapor. So that is also a simple definition of specific humidity. So that is clear. And if you see the second option, that is temperature to which an air parcel must be cooled at a constant pressure to become saturated. So this is nothing but what ma'am has explained it as dew point temperature, right? So dew point temperature, so these all we'll be using in our problems. Okay, dew point temperature TD, the temperature at which, so the definition is given here itself, it is a temperature, so it is a temperature at which the air parcel must be cooled at constant pressure or constant to become saturated. So temperature at which air would become saturated at a given specific humidity. To show the specific humidity only we are saying in terms of constant pressure. Why we are calling it as a constant pressure or constant or given specific humidity, that I will be telling you when we are solving questions, because there is a relation why when pressure becomes constant, how we can say that the relative humidity or the specific humidity becomes constant. That we will be seeing in the problems. Okay, so we can give the definition two ways: the temperature to which an air parcel must be cooled at a constant pressure or a given specific humidity to become saturated. So this is nothing but dew point temperature. So that is also wrong. This is dew point temperature. The third option is the ratio of actual vapor pressure to the saturation vapor pressure at the same temperature. So this is done. So that is vapor pressure we are not so that is nothing but relative humidity, right? So relative humidity from the term itself, it is from the the word itself, it is clear, it is relative to something. So we have the humidity of the air now. So relative, so in comparison to the maximum or the maximum moisture the air can hold, what is the humidity now? So that comparison is given by relative humidity. The relative to the maximum the moisture or water vapor the atmosphere can hold at that particular temperature, what is the how much portion or how much ratio or how much percentages of that is being filled now, or that is present in the atmosphere now. That is nothing but the relative humidity. So relative humidity is the ratio of actual vapor pressure to the saturated vapor pressure, right? So that we denote it as by letter RH. So RH is nothing but vapor pressure, that is the actual vapor pressure by the saturated vapor pressure, right? So before I define this, you know that it is clear that it is clear, right, what is a vapor pressure? What do you mean by vapor pressure? Okay, so vapor pressure is nothing but the pressure exerted by vapor in the atmosphere. Right, the atmosphere, we know there are vapor and also the other gases. Among that, what is the pressure exerted by the vapor alone? That is called vapor pressure. So at a temperature, at a particular state, the atmosphere will be having some vapor pressure E, and the maximum at that particular, it can, at particular temperature, it can hold is ES. So that ratio is relative humidity. So the third option is correct. This is the correct definition of relative humidity. And the final option is the partial pressure exerted specifically by water molecules within a mixture of dry air gases. What is this? What does the option 4 represent? Can anyone say? The partial pressure exerted by water vapor within the mixture of dry air gases. Uh, this is nothing but what we just said, na, vapor pressure. So vapor pressure, why we are calling it as partial pressure? That is because there are multiple multiple fluids, so multiple gases are there. Among that, the partial pressure exerted by the water vapor alone in a mixture of within a mixture of dry air gases. So when water vapor is mixed with other dry air gases, it combinedly forms the moist air. In that, how much pressure is exerted by the water vapor alone? That is called the vapor pressure. Okay, so the D option is the definition for a vapor pressure. So the motive of this question is just to make you understand of each of the term. What is relative humidity, what is specific humidity, what is dew point temperature, and what is meant by a vapor pressure. Okay, so the correct option is C. So so the next question is, it is related to the precipitable water. So in the lecture, if you have seen, once we uh, once we dealt with all these important terminologies, then we tried to define these terminologies at different levels of the atmosphere. If we are given the values of these terminologies in the ground surface, near to the ground surface, we tried to quantify them at some 2 kilometers above or 1 kilometers above. Okay, so we did all this with the help of a atmospheric column. We considered our atmospheric column, and using that, on that basis, we defined everything. That if we are given with the data for the ground surface, we were able to find these properties at any height, at any elevation. Right. Now, after that, we did one more thing within that atmospheric column. We tried to quantify how much precipitable water is there. So there is moisture content within that particular water column. There is moisture. So how much amount of precipitable water is there within that atmospheric column? That is also we saw in the previous week lectures, right? So this through this question, one thing I wanted you to make clear is what is a static atmospheric column. So the static atmospheric column is nothing but it's a frame of reference. So whenever we to define RTT, we made a control volume frame of reference, right? So static atmospheric column is nothing but we are assuming a frame of reference, or we are fixing a frame of reference there. So if I could draw, so this is the atmosphere. I am interested only in this particular area. So this particular height I am interested in. Okay, so it has an area A, right, and it has some height Z. Okay, so I am trying to analyze the atmosphere in this particular frame of reference. So only this much area or this frame of reference I am taking. So atmospheric column is nothing but it's a frame of reference. So now I want to find the total precipitable water which are present within this particular frame of reference of the atmospheric column. So for that, what we saw in the lectures is that we considered two height, that is one close to the one at a distance of z1 section 1, and another height at a height of section height 2, that is z2 elevation, right? And between these two we considered a small elemental strip, right? So we considered a small elemental strip here which had a thickness of dz. So this is the same procedure that we did for a controlled volume, that we are repeating for another frame of reference, instead of we are saying as a static atmospheric column, right? And if we want the total, so we want the mass of moisture, within this control, within this strip. If we know, if we can integrate this to get the total mass or total precipitable water within this particular control volume or the atmospheric column, right? So if I want to write the expression for that, so the mass of the air in the strip of height dz is equal to, mass is nothing but volume into density. So here we are dealing with air, so density of air into volume is nothing but area into height, right? So the area is A, that is already given, and height is dz. So we have the amount of water vapor or amount of air in this particular strip. Now if we want the total amount, the mass of water contained in air, so we got the volume of air. So in this particular strip we have an volume of air equal to density of air into area into dz. Now we need to find out in this volume of air how much is water vapor. So that is given by specific humidity, right? Specific humidity is nothing but how much moisture is there in the atmosphere. So if we multiply specific humidity with this particular term, or specific humidity, one more definition that we saw is density of water vapor into density of air. So if I use that particular definition, we can write this as rho A dz, that is the volume of air into specific humidity, right? This will give us nothing but the mass of water contained in the air. So this much amount of mass water is there, moisture, precipitable water is there inside the strip. So if we know that, if we want to if we know this particular thing, if we want to know total amount of water in the entire strip, we just need to integrate this, right? So the integration we will be doing like total precipitable water m p is equal to integral from, say, the height through z we are saying from the bottom to the top, that is density of air A qv dz. So this integration we saw is pretty like, if we are not doing it in a, to approximate this with this continuous integral, we are discretizing, right? So to discretize, when we discretize this, what we'll be doing is we'll be dividing this particular column into very small elements of delta z thickness. So the finer we divide, better will be our answer, in that way. Okay, so what we are doing, we are basically dividing this strip, that is d uh, mp is equal to uh, so this we already so so delta mp, so this is dmp delta mp, so dou we are changing it to delta, we are discretizing, and it will be rho a average into q v average into a into delta z. So what we are doing is basically we are taking strips of thickness delta z. So say for example, consider a thickness, a strip which is having a delta z thickness within the water column. Okay, so there will be a density at this height and there will be a density at this particular height, right, above and below the strip. That is the boundaries of the strip, and there will be a specific humidity at this height and there will be a specific humidity at this particular height. So here this rho a bar is the average of these two heights, that is rho a1 plus rho a2 by 2, and qv bar is nothing but the average of qv1 plus qv2 by 2, right. So we are trying to simplify this, we are not doing going for a continuous integral, and we are discretizing it, and when we discretize we have to divide it into finer elements of thickness delta z, and this delta z while discretized, the more finer we make, better will be our, like more accurate will be our answer. Okay, so there we are taking, whenever we are discretizing, we need to take the average air density and average specific humidity within that particular delta z. Okay, so in this options, if you see in this particular question, they were asking us the equation for the incremental mass of water vapor. So that is given by option rho into delta z is given by option A, right? Yes. So the question is the incremental mass of water vapor in a small strip of height delta z per unit area it may be considered. So actually there should be a thickness A into area A, but maybe per unit area, where maybe the question they have considered per unit area. They should have mentioned it, but actually area should be there. If we take it's a unit area A equal to 1 unit, this may be assumed, then the equation is option A. Okay, so all the others are wrong. So basically you need to understand how we came up to this particular equation, and then why then we discretized this and came up to a simplified format. But here we need to take the average q rho a and qv. Okay, so next is a theory question, that is the two fundamental mechanisms required for formation of precipitation are lifting of moisture and uh, anyone can answer this? Yes. So the two fundamental, to the two main basic mechanisms for formation of, so you should be clear with the terms formation of precipitation. So in the lectures you saw how the formation of precipitation takes place. So the two main mechanisms are, first mechanism is lifting of air, the second mechanism is nothing but nucleation. Okay, so If you see the other options, frontal, orographic and convection, do you know what are they? What we can call them collectively? Yeah. So they are nothing but, so there are fundamental mechanisms are two. First is the lifting of air mass. The second one is nucleation. So I'll go in the order. So the air mass lifting, that is the the air mass has to reach the atmosphere, right? So how this lifting takes place? The mechanism of lifting. So mechanism of lifting of air mass. This can be divided into three. This is, under this comes frontal lifting, orographic lifting, and convective lifting. Okay, so basically the question was, what are the fundamental two mechanisms for the formation of precipitation? So that are nothing but lifting of air mass and nucleation. So what is nucleation, that I will come after this. So before that, the first process that has to happen is the lifting of air mass. So lifting of air mass can happen in three ways, that is frontal, orographic and convective. So we can see, quickly see what are these three. So frontal is nothing but if you take a surface and if you see there is cold air in one side and warm air is there in the other side. Warm air is in the other side. So there is a surface in between, there will be a clear division between these two, right? So that particular division, this particular division is called front. And if you see the wind movement, if we see the movement of air, if the cold air is moving towards the warm air, then the front that is formed is called a cold front. So we have cold air in the left and the warm air in the right. If the cold air is moving towards the warm air, the front or the division or the separation between those two formed is called a cold front, right? So what happens is, so the cold air moves towards the warm air, and the due to the cold front, the warm air. So due to the cold front, the warm air here rises up along the cold front, and it goes up, and clouds will be formed, and precipitation, condensation happens, and precipitation will happen. Okay, so similarly, so here the uplifting is due to the front formation. Front means there is the separation between the cold air mass and the warmer air mass. Okay, and similarly there can be another the opposite of this, that is when what we say, when the warmer air is flowing towards the cold air, so then the front that is formed is called the warm front. Warm front will be formed when warm air is flowing towards the cold air. Okay, so another thing you can remember is, when this happens, when cold front happens, in this particular case, when cold front happens, the the precipitation that we'll be receiving will be intense and in a smaller area. It will be intense, intensity will be very high, and it will occur in a smaller area. And when this particular thing happens, that is when warm front happens, when the warm air is flowing towards cold area, cold air, then what happens is it will be less intensive. Rainfall that occurs will be less intensive, but it will be spread over a larger area. Right. So this particular airlifting mechanism happens due to front formation. Front formation is nothing but when a cold air mass meets a warm air mass, a warm air mass meets a cold air mass. So the thing that you need to remember is this particular mechanism of airlifting is called the frontal lifting, and also this particular separation is called the front. And what are the types, what are the characteristics of the precipitation that happen in these particular two fronts? So that is frontal precipitation. So let's move on to the second type of airlifting mechanism, that is orographic precipitation. So here basically how the uplifting happens is due to the terrain. So if you take an example, if we can show with a figure, so there's some water body here and there's a mountain, right? So when the warm air, the evaporation happens in the water body. This is a water body, evaporation happens, so there are more warm air is there here. So this warm air will, when it collides a terrain or a mountain, something like a mountain, so along the mountain, due to the wind action, it will move up and it will reach the atmosphere. So and the clouds will be formed and it starts raining in this particular side. So this is called orographic precipitation, right? So one of the best example is if you see if in our India, in the Kerala side, we receive a lot of rainfall, right? That is because of the presence of the Western Ghats. So we have the Western Ghats mountains, and when the warm air from the ocean, that is from the Arabian Sea, when the warm air comes, it collides with the these Western Ghats and it rises up, and the Kerala region will be getting the Western Ghat region, that Kerala side will be getting lot of rainfall. So that is nothing but orographic precipitation. But when this happen, the this particular side, after this moist all after this all the uh, clouds get precipitated, then the dry air will be moving to this particular side. Dry air or the air with very low moisture will be moving to this particular side. So we will be having dry air. So in this particular region we will be receiving very low rainfall compared to the other side. So this particular side is called the rain shadow region, or leeward side, and then this particular side where the precipitation happened, that is the Kerala side, that is called the windward side. So windward side means in this side the wind is coming, right? The moisture from the water bodies, the wind is in this direction, that is why it is colliding the mountain, it is going up and forming clouds and raining over there. And the other side is called the other side is called the rain shadow region or the windward side, leeward side. So next type of precipitation is the convective precipitation. So the convective precipitation is nothing but, you consider a plain area, a plain water body or a river or a lake, right? So there, if you consider a plain water body, a plain area which is having a water body like a river or a lake, Actually what happens here is due to convection. So convection, you know, right, in the heat energy transfer, that particular process is called convection. The heat will move from a higher energy to lower energy. So when when this is convective precipitation, when this water body get heated up, it gets evaporated and more water vapor will be formed. So when it heated up, here the warm air will be there and it will rise and it will form clouds, and in the upper layer, the upper layers of atmosphere, the temperature is less, so it cools down and it will fall as rain. So this is basically called a convective precipitation, right? So here what we can notice that this particular type of precipitation, it will be followed by, this actually happens in a hot and humid area. Hot and humid. So what do you mean by hot? Hot is nothing but it should be, there should be a strong sunlight or strong heat energy should be there, right, to evaporate that much quantity of water. So it should be in a hot area. And humid means it should have plenty of it shouldn't be arid, it should have plenty of water. The atmosphere should have plenty of water, it shouldn't be water deficit, it should be water surplus. So such precipitation can take place only in a hot and humid area. And the characteristics of precipitation here, it will be high intensity and it will be accompanied by thunder and lightning. So thunder and lightning are accompanied by convective precipitation, and it has very high intensity and it will occur in a hot and humid area. Okay, fine. And coming to the our answer, that is nucleation. So now we know the air masses got lifted up and it has reached the atmosphere, right? So if the air, so once it has reached the atmosphere, it has to form clouds. So to form clouds, that process is called, and to form clouds and then the condensation to occur, that particular process is called nucleation. So nucleation is nothing but the process of condensation to occur. So the air masses have lifted up and it has reached the atmosphere. Now the process of condensation to occur, uh, it requires condensation nucleus. Condensation nucleus is nothing but there should be a medium, there should be something for there, so that the water particles or the vapor present in the atmosphere, the vapor which have lifted up and reached the atmosphere, can combine, right? They can combine and form cloud. So for that it requires a medium, or that we are calling a condensation nucleus, around which the water molecules can attach. So these example of these condensation nuclei, or the particles around which the water molecules can attach and form the clouds, these are dust particles which are floating in the atmosphere, they can act as a condensation nuclei. Then we have the aerosols, which are the pollutants. Aerosols, they can act as a condensation nuclei, or sulfur and nitrogen compounds. So these compounds are present in the atmosphere. So when the water vapor rises up by these three mechanisms that we just explained, when these compounds are there, when they meet these compounds and they just accumulate and form clouds, and then the precipitation will occur. So the formation of precipitation is two steps. One is this, the lifting of air mass by different mechanisms, and the second one is the nuclear. So that is nucleation. So that is why if you see two locations, if you know, or we in the previous question we saw all the terminologies which we can define at different levels of atmosphere, and we took two different regions, one in the Kerala region and one in somewhere in New Delhi. Then we are seeing that all the atmospheric parameters are remaining the same. Still it rained in Kerala, but it didn't rain in some other location in Delhi. What may be the reason? That may be because the condensation nuclei were present in were abundant, or were present in large volume in case of Delhi when compared to Kerala. So that is why, even if all the atmospheric variables are same, still for the precipitation to occur, this particular mechanism should be carried out. That is, there should be some condensation nuclei present in the atmosphere. Okay. So in case of artificial rain and all, so if you have seen in the paper, when to in Delhi, if we have the pollution issue, and we have seen in the like the we are going for something called an artificial rain to reduce the pollution, right? So in such cases, we are spreading such nuclei in the atmosphere. You can see, right? With the help of aircraft, we are trying to spread these particular condensation nuclei in the atmosphere, so that the water molecules can uh, get a medium or a condensation nucleus, so that they can accumulate and the rain can happen. Okay. So our answer is nucleation. So one is the lifting of air. All other three are different mechanisms of lifting of air. Okay. So we'll come to the final question of MCQ type. So this is related to the terminal velocity. So a drop is falling. So now the rainfall, the air mass got lifted up. It reached the atmosphere. Condensation nuclei were present. It formed the cloud. Now it is started falling from the cloud to the ground surface. So when it falls, the water droplets, initially it is similar to the problem in physics. We say, we are dropping a spherical ball, we are dropping. Initially it was in rest with the cloud. It dropped, then the velocity increases. It initially it has zero acceleration, then it will be moving under the acceleration of gravity, right? So after some time, say because of all the forces acting on the particular water droplet or the raindrop, it will attain a zero acceleration. That is, all the forces get balanced. So that particular equilibrium, it will be having a constant velocity. Zero acceleration means velocity is constant, right? Zero acceleration means either the body is not moving or the velocity is constant. That constant velocity it will attain, that particular velocity is called the terminal velocity, right? So in this question, they are asking when the body has reached that equilibrium. Now the raindrop is falling under terminal velocity. Which of the following are true? That is, we have to just write the force balance of that, or the force balance of that particular raindrop that is falling, right? So we'll quickly go through this. So basically, we have the raindrop. So we have one force is familiar is obviously there, that is the weight. So weight is given by Fg, so that is the gravity force, right? And opposite to that, or in the upward direction, we have the buoyant force. Buoyant force you all know, right? Buoyant force is nothing but it is related to fluid. Whenever we like if we immerse something into a bucket of water, we can feel a force that is exerting back. It is pushing up. If we insert a cup into a bucket, some force is exerted back. That particular force is called buoyant force. So that will be acting opposite to the gravity. So here the fluid is not water, the fluid is air. So air will be having a buoyant force in the upward direction, and the buoyant force is defined as it is equal to the mass of fluid displaced. Here the mass of fluid is mass of air displaced, right? And then we also have the friction. There will be so the atmosphere is not smooth, right? It has very large number of particles. So the when the raindrop falls, it will be colliding with all those particles, so it will exert a drag force. So that will be also opposite to the motion, that is opposite to the gravity. So that is along the surface it will be having the drag force, that is we are representing by Ft. So if we write the force balance, if when it's in equilibrium, that is when the velocity is constant, Vt is constant, uh, that is in the downward direction, so the motion is in this particular direction. So Fg minus Fp minus Ft is equal to ma, we can write. So ma here, acceleration velocity is constant, so m dv by dt, that is equal to 0. So here what we can write is Fg Fp is equal this particular, this is Ft, right? So Fg will be equal to Ft plus F buoyant drag and buoyant force, right? So gravity force is balanced by both the summation of both the what we say the drag force and the buoyant force, right? So the answer is C. So the correct answer is C. These all are wrong. So nothing but the also in the lecture man has solved this particular derived the equation for the terminal velocity also, that we will be seeing when we are dealing with the numerical type questions. Okay, so we have 45 more minutes. We can start with the numerical type questions. So numerical type questions, how I have framed is initially we need to know there are many relation between the those 5 or 6 terminologies that we saw, right? We saw 5 or 6 terminologies related to the atmospheric water. So so these were the different terminologies. These terminologies all are related to each other, so there are different relations that we need to understand. So the initial numerical questions will be easy. So the main intention is to make you familiar with these relations. So once that is done, then we'll go on to the complicated questions. Okay, so we can start with the first question, that is calculate the density of air assuming that the total pressure is 100 kilopascal and air temperature is 27 degrees Celsius and gas constant is 287 joules kilogram Kelvin, and we need to report the answer in kg per meter cube and round it to 3 decimal places. So I think your final exam in the NPTEL exams, those who are registered for exam, it will be also having the similar questions. I will confirm it. It will be also having a similar question in the sense the similar pattern. You'll be asked to report the answers in this particular unit and this particular decimal places. Okay. So the first question is to calculate the density of dry air assuming that total pressure. So we need to find the density of dry air, that is rho T. Yeah, rho D we need to find assuming that the temperature is given. This is question mark. So temperature is 27 degrees Celsius and gas constant is given, that is Ra. Gas constant for air is equal to 287 joules kg Kelvin, and pressure is also given. Pressure is 100 kilopascal. So in this particular question I want to introduce the first final exams. We have exams there, assignment questions or not. Actually I'm not familiar with the final exam, how it will be. Only thing I know is, like, from the knowledge of my friends, is that you will be asked to write the exam in some center. So regarding the questions and the pattern of the questions, I will let you know in the next class. Okay. And so basically here we'll be see the first relation. The first relation that we want to be applying, what we'll be dominantly applying in atmosphere, will be the ideal gas law. So ideal gas law is something that we learned in, like, in plus 1 or plus 2, right, in your class 11th or 12th. So that is partial pressure exerted by air in a mixture of air is equal to density of that air into gas constant, universal gas constant, into temperature. This is nothing but this is the first expression. So first thing we need to remember is this particular relation that is given by ideal gas law. Okay. So here we know, in this particular term, we know the pressure is given to us, we have Ra given to us, we have T given to us. Okay, only thing is to find density. So we are going to find rho D. Rho D is equal to P by Ra into T. So P is 100 kilopascal. So to convert to pascal, we have to multiply it by 1000, right? And this is 287 joules per kg per Kelvin. Okay, so everything is in SI, and the temperature here is given in Celsius, degrees Celsius, right? Temperature is 27 degrees Celsius. So temperature in Kelvin will be 27 plus 273.15. This conversion you know, right? Degree Celsius to Kelvin, 273.15. That will be around 300.15 Kelvin. So you can substitute that here, 300.15 Kelvin, everything get cancelled, and everything in SI unit. So you will be getting it in SI unit, right? So if you solve this, it will be approximately around 1.1608. So the unit is, this is density, right? So unit will be kg per meter cube, and I have put everything in SI unit. Pascal is the SI unit, right? Newton per meter square. So we'll be getting this in. So this is Newton per meter square, and we have in the denominator we have joules per kg Kelvin into Kelvin. So Kelvin gets cancelled. Joules will be Newton. So joules we can write it as force. into displacement square Newton meter. So these all get cancelled and 5 Newton per meter. Then finally what? So this joules we can write it as Newton per meter. This will get cancelled. Newton gets cancelled. What remaining? It will be kg per meter cube. So they had asked us to report the answer in 3 decimal places. So the entry that you need to make will be 1.161 kg per meter cube. This is our final answer. So only point of solving this question is to give you a recap of the ideal gas law. The relation is partial pressure exerted by the air is equal to density of air rho, that is here it is dry air, density of dry air into Ra, that is gas constant for the air, in multiplied by T, that is temperature. That should be in Kelvin, or depending on whatever the unit of Ra is given. Okay. So one relation is done. So this you have to remember, that is the ideal gas law. The second is calculate the specific humidity of air mass that has a vapor pressure. So vapor pressure is 1.5 kilopascal and total atmospheric pressure is 95.05 kilopascal, and we have to report it in kg per kg. Kg per unit means unitless. So specific humidity, you know, it is unitless, right? And we have to round off to 4 decimal places. Okay. So basically we need to find specific humidity, that is QV is question mark, and we have given vapor pressure. So vapor pressure of an dry air mass. So there is actual vapor pressure is given, that is denoted by E, right? Vapor pressure is denoted by E, that is 1.5 kilopascal, and the total atmospheric pressure, that is denoted by P. Atmospheric pressure is denoted by P. Total pressure exerted by the atmosphere is, that is vapor plus the other gases, that is equal to 95 kilopascal. 95 kilopascal. So the relation that we will be using here is E by P. Yeah, QV will be, so there is a relation between specific humidity with the actual pressure and the vapor pressure. The relation between QV as a function of E, actual pressure, and the vapor pressure and the actual atmospheric pressure. So that is given by 0.622 E by P. So this is the second relation which I want to make you familiar to you. So you know what is specific humidity, that we already saw the definition of each and every term we saw in the our MCQ question, and now we will be familiarizing with the relations of between these terminologies. Then we will go to the complicated questions. Okay. So this, so everything is given, you just have to substitute. Specific humidity will be equal to 0.622 into E is 1.5 and kilopascal, and this is 95 kilopascal. So guys will be cancelled. You will be getting it at around, approximately it will be around 0.00982. So this is, usually we write specific humidity in this unit, that is it is unitless, but we write it as kg per kg. That means it is the ratio of mass of moisture to the total mass of moist air, right? So mass of moisture in kg, total mass of moist air is also in kg. That's why usually we denote it in by the representation kg by kg. The thing that you have to understand is there is 0.00982 kilograms of water vapor in 1 kilogram of moist air. That is the understanding you have to see, you have to get by seeing this figure, or seeing this figure value for the specific humidity. This much moisture is there in 1 kg or 1 unit of moist air. Okay, so we have been asked to round off to 4 decimal places, right? So it will be, the final answer will be, the answer you need to report should be 0.0098. So this is the final answer. Okay, 0.0098. No, kg per kg, no? It has no unit. Specific humidity has no unit. Yeah, that's what this particular dimensionless quantity does. Just says that for 0.0098 units of moisture is there in 1 unit of moist air. So if we write it in words, 0.0098 units, it can be kg, it can be gram, it can be kilo, anything, units of moisture, or I can write it as water vapor in 1 unit of moist air, or I can say atmosphere. So this is the meaning of this particular quantity in kg per kg. Okay, so this relation you have to remember, which connects specific humidity with the vapor pressure and the total pressure. Okay, so we will move to the next question, that is, assume the air temperature at sea level is 35 degrees Celsius. If the environmental lapse rate is constant at 0.65 degree Celsius per kilometer, calculate the air temperature at a height 3000 meter, that is 3 kilometer above, and our answer should be in degrees Celsius. So here I just want to introduce to a term called lapse rate. So lapse rate is equal to 6.5 degree Celsius per kilometer. So lapse rate is nothing but as we go up in the higher altitude, the temperature will be decreasing, right? That is clear. Temperature will be falling when we go up to the high altitudes, right? So the rate of fall, how much lapse in temperature happens, that rate of fall is given by this particular lapse rate. That is, if you move 1 kilometer, there will be a fall of 6.5 degrees Celsius, right? Degree Celsius. So for this first, so the drop in temperature delta T is given by this particular lapse rate into delta Z. That is how much altitude we traveled, from which particular is altitude to till what altitude we traveled. So the lapse rate is 6.5, delta Z is from the sea level. If I take the sea level as 0, so I am taking sea level as Z equal to 0. From sea level I will travel to an altitude of Z equal to 3000 meter or 3 kilometer. So delta Z is nothing but 3 kilometer, right? So the lapse rate is given per kilometer, so I substitute in 3 kilometer. So this will be around 19.5 degrees Celsius. So I traveled 3 kilometer up, so there will should be a fall of 19.5 degrees Celsius. Total fall of 19.5 degrees Celsius compared to the temperature at the sea level. So questions you're solving in the class are taken textbook or random, and believe these questions are given given by professors from IT quality. No, in the problem solving sections, what we'll be doing, we'll be framing the questions so that we'll be getting an idea of the entire lecture. We'll be so I'm responding to a comment which I got in the chat. So basically we'll be trying giving a recap of all the formulas and all the concept that we have learned in the previous class, and then we'll be moving on to the complicated questions. So I know in this particular course there will be students from all the categories. So for to make them understand in an easy way, we start with the simple concepts, and we have the difficult questions coming up in the coming sections. Okay, not coming sections, the coming questions will be more difficult. So before handling those such questions, I wanted to make sure that these basic concepts are clear. Okay, so there's a total fall of 19.5 degrees Celsius. Therefore the temperature at a height 3000 meter will be 35 degrees Celsius minus 19.5. That will be 15.5 degrees Celsius. Okay. So basically, lapse rate is nothing but the rate at which the temperature is lapsing. So in this question, I just wanted to highlight that is, if you are given the temperature at a ground at any level in the atmosphere, and if you are asked to find the temperature value for any of the at any elevation, given that lapse rate is given, you can do it using this particular relation. And next we'll be seeing, if we have the temperature value at other locations, how we can find the other parameters that we also other parameters of the atmosphere that we just saw in the MCQ sections. Okay, so the next question is, so three relations clear. One is the lapse rate one, another relations between E and P, another is the ideal gas law, right? So next question is, based on the conditions on the previous questions. In the previous question, so we were given what is the condition at the sea level, what is the temperature of the sea level, what is the lapse rate, right? And we also found the temperature at 3 kilometers above. And the same conditions where the surface temperature is 35 surface temperature is 35 degrees Celsius and the lapse rate is 6.5. Calculate the atmospheric pressure at altitude of 3000 meter. Assume the surface pressure is 101.3 kilopascal and the acceleration due to gravity is 9.1 meters per second square. The gas constant is also given 287 joules kg dot Kelvin, right? So basically in this question, now we already know how the temperature, we were given the temperature at the ground surface. Now we can calculate the temperature at 3 kilometer, right? Now we are given the pressure at the ground surface. We know the temperature, we found it in the previous problem. How we can get the pressure at a 3 kilometer elevation? So that is what we are going to solve in this particular problem. Okay, so through this question I wanted you to introduce to this particular relation. If we have given a particular pressure at one particular elevation, the pressure at any other elevation can be found if we know the temperature there, right? The relation is P2. P2 is the temperature at location 2. P1 is some location that we know, is into T2 by T1 whole raised to n, right? And this n is nothing but the exponential term is nothing but it's a constant. That constant depends on g, that is acceleration due to gravity, that is a constant alpha and ra. Okay, so to this question I just wanted you to give a recap to this particular relation. If we know the pressure at one particular elevation, how to find the pressure at another elevation provided you know the temperature. So if you know the temperature at the ground surface or the temperature at the surface where we know where the pressure also, if we have the lab state we can find T2, right? T1 we know, T2 we already found out because we know the lab state, and also we know G we know, Ra we know, and alpha is the lab state. We can get the expression for the n, and if we substitute in this we will be getting the pressure at this particular elevation. And also you know the relation, right? As we go in higher altitude the pressure will be lower, so the P2 will be always lesser than P1. Similarly temperature also, temperature at higher altitude will be lesser than the temperature at the lower altitudes, right? So just to check whether if you are not going wrong in any calculation or somewhere, you always check this results. Whenever you are finding the pressure at some altitudes higher than the altitude which you have the data, it should be lower. So that logic every time should be there in your mind. Okay, so here we need to find P2. So before that we can go in a systematic way. We can find n. N is nothing but 9.81 divided by alpha is 6.5 degree, alpha is 6.5 degrees Celsius per kilometer. That will be same as 0.0065 degrees Celsius per meter, right? So 0.0065. You have to convert this into meter because RA is given as joules, is in SI unit, 287 joules kg per Kelvin. So if you do this you will be getting n value has, that is exponent value as 5.2586. So if we have now we have exponent value, then we can directly find P2. P2 is nothing but P1. So P1 is how much? P1 we had P1 as 100.1.3, right? 100.1.3. It is in kilopascal. We will get our answer in kilopascal itself. Into, we have a ratio of temperature. So the ratio is temperatures are given in the previous question. We have the temperatures, then the sea level is 35 and 15.5. So both we need to convert it to Kelvin, right? So here our gas constant was in Kelvin. So here also the temperature, the conversion you have to be clear. You have to convert both the equations, both the temperature into Kelvin. So if we convert, it will be 288.65, that is T2, and T1 is 308.15. So this will be coming around 71.79 kilopascal. Right. Okay, so we have to round it off to two decimal places. This will be 79.79. And such questions, there will be a range. It doesn't matter to get an accurate value. There will be a range where if you get the value within that range, your answer will be correct. Okay. So through this, just so two things are clear. If you have the temperature and pressure values at any particular location, and if we are given with the lab state, we can get the pressure and temperature at that particular another location. Okay, so let's move on to the next question. So here the question is, so we need to calculate the relative humidity. So what is relative humidity? We already saw in that MCQ question. That is the vapor pressure by actual vapor pressure by the saturation vapor pressure. Saturation vapor pressure is nothing but the maximum vapor pressure at that particular temperature. So calculate the relative humidity of the air parcel that has a dry bulb temperature of 25 degrees Celsius. So dry bulb temperature is nothing but it's the actual atmospheric temperature. So the atmospheric temperature, atmospheric temperature is also called a dry bulb temperature of that air parcel. So the dry bulb temperature of the air parcel is nothing but the actual temperature of the atmospheric temperature, and its dew point temperature is given as 15 degrees Celsius. Okay, so the actual temperature is 25 degrees Celsius and dew point temperature is 15 degrees Celsius. Utilizing the concept of actual vapor pressure of an air is equal to the saturation vapor pressure at dew point. So utilizing the concept that you're familiar with this concept of the lecture, right? The actual vapor pressure of the air is equal to the saturation vapor pressure at the dew point. So this would be clear with the help of that plot, right? So ma'am has explained you with the help of this plot. That is, there is, before I make the plot, so this is that particular relation where the saturation vapor pressure is related to the temperature. So if we make that particular plot, so we have the saturated vapor pressure in y-axis and we have the temperature in x-axis. So it will be something like this, and this particular curve is defined only for ES, that is, we are calling it as vapor pressure. For all vapor pressure, this curve is not defined. For saturated vapor pressure only, this particular curve is defined, right? And it is given by this particular relation given in this question. So the concept they are telling in the question is, so we have the dew point temperature TD, right? And we have the actual vapor pressure. So it corresponding to that, we have a vapor pressure E, and we have the saturated vapor pressure ES. Corresponding to that, we have another temperature T, right? So the concept is the actual vapor pressure, that E of the parcel is equal to the saturated vapor pressure at the dew point. So at the dew point, whatever the pressure is, whatever the pressure means, if it lies here, lies in this particular curve, it is called the saturation vapor pressure, right? So this particular pressure, saturation vapor pressure, that is the actual vapor pressure of the that will be actual vapor pressure of the air parcel, this E, right? So this particular concept we are using, this particular concept we are taking from this plot, and we will be using this to solve this particular question. So one more time I'm repeating, this particular curve is defined only for this particular curve is defined only for ES values, that is saturated vapor pressure. So we have a temperature called TD. The saturated vapor pressure corresponding to that is the actual vapor pressure of that air parcel. Okay. So we need to find the relative humidity, right? So actually this is a question is simple. Only thing you have to understand this particular concept through this graph. So we have the saturated vapor pressure, so ES. So before that we know the formula of relative humidity. So relative humidity RH is nothing but E by ES. So only thing you have to remember is E is equal to ES at dew point temperature. Dew point temperature. So this concept should be clear from this particular graph. Then the question is simple. Then the question we can convert it as, this is ES at dew point temperature is how much? It is mentioned as 15. 15 divided by ES at the saturation pressure, saturation temperature, that is 25. So you just have to substitute these values in this particular equation. So this in this particular equation, if you substitute this, we will be getting, just a minute, ES at 15 will be equal to 0.611 exponential of 17.27 into 25 into 15 divided by 237.3 plus 15. So this will be coming around 1.705 kilopascal. Similar way, if you can find for ES25, it will be 0.611 exponential of 17.27 into 25 divided by 237.3 plus 25. That will be around 316.9 kilopascal. And if you substitute this, our RH will be equal to 1.705 divided by 3.169. It will, you have to now represent the answer in percentage, right? So that will be equal to that into 100. If you want to put in percentage, that will be equal to 53.80 percentage. So that is the relative humidity. So here the key concept is that if we want the actual pressure, vapor pressure will be equal to the saturation vapor pressure at dew point temperature. So this is the actual vapor pressure E. Our air pack, the air parcel is at temperature 25. So we need E value. So E, what we do, we draw a horizontal line, we bring it to this particular equation in this particular curve. And if we so this particular temperature is called the dew point temperature. This we already know. If we substitute that, we will be getting E. Okay. So we have 8 minutes. So next question is something related to the rainfall, that the terminal velocity. So we already saw the equation. So we didn't derive the equation, but we know we know the formula for this, right? Formula for the terminal velocity. So the formula for the terminal velocity. So a small raindrop, uh, as the terminal velocity is already given at 4 meter per second. Calculate the diameter of the raindrop. So diameter is what we need to find. D is what we need to find. So we are assuming it to be spherical, right? So we will assume in this derivation we assumed it as a spherical raindrop. Then we derived. So here also diameter they are asking. So we will be assuming it as a spherical raindrop. And drag coefficient is given. This is for the drag force and the friction force, and the acceleration gravity value is given, and the ratio of density of water to air is 850, and we have to report our answer in mm. So the formula for finding the terminal velocity v is given by square root of 4gd into 3cd rho w by rho a minus 1. You can simplify that into in this particular form. Okay, so in this, so this is the equation for the terminal velocity. If you can, we can simplify it into this particular form. In this equation, Vt is given with us, G is given, D is something that we need to find, CD is given, this particular ratio is also given. This is the substitution is left, right? So I can write diameter has 3cd Vt square divided by 4g rho w by rho a minus 1, right? So we just have to substitute the values. So 3 cd is the drag coefficient, that is equal to 0.6. Vt, we have given terminal velocity in meter per second, so it is SI unit, so I am keeping it as it is, 4 square. Denominator we have 4 into 9.81, everything is in SI till now, and this ratio is 850 minus 1. So everything is SI, so I will be getting in meters, right? So if we solve, the numerator is around 28.8 divided by denominator 33314.76, which comes around 0.000864 meter. So this is the diameter of the raindrops, and the question they have asked us to report it in mm. So this won't be the answer. The final answer will be this into 1000. So that will be equal to, and we have to round off to 2 decimal places, right? So it will be equal to 0.86 mm. So if you can see here, this particular value is still less than 1 mm, right? So we saw in the lectures, like if it is more than 1 mm, the raindrop will take a oval shape. It won't be spherical. So unless it is less than 1 mm, we can assume it as spherical, and we can solve these questions. These equations we can use when it is, once it is oval in shape, then we have to find the equivalent radius. There is a formula for that also. We have to find the equivalent diameter, right? Then you have to apply this particular equivalent spherical diameter of an oval shape. You have to find and then apply this equation. Okay, so we'll move on to the final question. So this is related to the precipitable water. So to do this question, we need to have all the formulas or relations that we saw in the previous questions. So basically how we are finding that we are given with the temperature at one particular location, how we are finding the temperature at a different altitude, how we are finding the pressure at different altitude, how these pressure and vapor pressures and the actual pressure related to specific humidity, and how the density is related to this. All this comes in this particular equation. So once you are clear with all the relations which all the equations that we solved before, once you practice such short questions, we will be able to solve this particular equation without any confusion. Okay, so the question is to estimate the precipitable water in the first 2 kilometer layer of a saturated air column. So precipitated water we have to find at the first two layer of the first 2 kilometer layer of the precipitated water column of ground area 1 meter square. So they have already divided the column into different layers. Each have 2 kilometer thickness layer, and we need to find asked to find in the first layer only. So only the first discretization we have to find. There are multiple discretization 2 kilometer, and the first 2 kilometer discretization we need to find the air column precipitable water. Okay, so assume the surface pressure is 98 kilopascal. So we have the surface pressure as, so I am calling the first down location as Z equal to 0, and there the pressure area is 1 meter square, and pressure P1 surface pressure is 98 kilopascal. Surface temperature is 32 degrees Celsius, that is plus 273.15, that will be around 305.15 Kelvin. So first I'll be making use of the first ideal gas law. So that's relation I think you are familiar, that is density we found using P1 by RA T1. This is the relation of ideal gas law, right? So from this we can find the density at the location 1. So density at the location 1 is given by, so why we are finding all this, because we know the expression for delta m, that is equal to delta m is given by the average density, that is average density of air into average specific humidity into delta Z into area is equal to 1, so that one be here. So this equation we know, so we need to find the average rho A and average. So rho A average will be rho 1 plus rho 2 by 2. So in this way we will get rho 1. So rho 1 will be nothing but, just we have to substitute is 98 into 10 to the power 3 divided by R is 287 into 305.15, that will be coming around 1.119 kg per meter cube. This is similar to the first question that we did today, right? And first numerical type question. And similarly rho 2 we can find, that is density at location 2 is equal to the height of 2 kilometer. Rho 2 will be P2 RA T2. So here the problem is we are not given what is T2 and what is P2. So P2 and T2 we already know from the previous questions. We know we can find if you are given a location, at particular location the pressure, temperature is given and the lab state is given, we can find T2, and similarly we can find P2 also, right? So for that we already got P1, so this we'll put in a hold, otherwise we can find it now itself. It's fine. So first we will be finding T2. T2 will be T1, that is T1 minus, so anyway the temperature will reduced, so whatever the temperature in T1 will be, that minus lapse rate alpha into delta Z, right? So T1 is 32 degrees Celsius minus 6 into 2. So that will be equal to 20 degrees Celsius. That is also equal to 293.15 Kelvin. T2 we got, right? Now what we need is P2. So P2, we know that relation. If we know P2 is given by P1 into T2 by T1 raised to a constant n, and that particular constant n is nothing but G by alpha into R, right? That is 9.81 divided by alpha is 0.006 into, that is by, I converted it per meter to 87. That will be around 5.697. So if I substitute that in this, P2 will be equal to P1 we already know, that is 98 into T2 is 293.15 and T1 is 287, and whole raised to n is 5.697, right? So P2 we'll be getting it as 77.95 kilopascal. So we got the pressure at 2. So this also we got. Now what is from T2 also we got. So we can find the density, right? Density at second location. Again we'll apply the gas law. So gas law if we apply, then it will be P2 divided by RAT2. So P2 is 77 9 into 1000 I'm doing, so it will be this much divided by RA is 287 into 293.15. that will be approximately 0.926 kg per meter cube. So this is the same concept. At a particular location pressure and temperature was given. Now we got at 2 kilometer altitude what is the pressure and temperature, given that we have the lapse rate with us. Okay, so we have density at rho 1 and rho 2 we got. So average rho will be equal to rho 1 plus rho 2 by 2. That is equal to rho 1, how much it was, 1.119. So if I substitute that, rho 1 will be, rho A bar will be 1.119 plus 0.926 by 2. That will be equal to 1.0225 kg per meter cube. Okay, so one term we got out of this. Delta Z is known to us, A is known. Now what is left is Q, that is QV, specific humidity at location 1 and 2. So how we can find the specific humidity at location 1 and 2? For that we will be using that particular relation of QV with pressures. That is QV is equal to 0.622 E by 622 E by P, right? So here the only unknown is E. E is nothing but the vapor pressure. So vapor pressure, so in the question if you see, perform the evaluation. So in the question if you see here, the air column is saturated. So this is important. They have mentioned that the air column is saturated. So the vapor pressure what we are having now will be nothing but the saturated vapor pressure, right? The air column is saturated, they mentioned in the question itself. So the pressure we are having now will be the saturated vapor pressure. So at both the location QV1 1 and 2 we know the temperature. So T1 we know, T2 we know. So if we want the saturated vapor pressure at T1, we have the relation we will be getting, and saturated vapor pressure at T2, that also will be getting, right? Because we directly have the relation. So that is given by the formula uh, ES1. So here S will be saturated. ES1 is equal to 0.611. This also we already used. This is the formula for that plot, right? 17.27 into S1, the temperature in degrees Celsius is 32. That is location 1, it is 32. Divided by 273 to 37.3 plus 32. That will be coming around 4.758 kilopascal, and ES2 will be similarly, if you substitute exponential of 17.27 into 32, and the other T2 was 20 degrees Celsius. 20 divided by 2, 37.3 plus 20, that will be around ES2 will be 2.339 kilopascal. So we have ES1 and ES2, so QV1 will be equal to ES1 by P1 multiply 0.622, that is equal to 0.622 into 4.758 divided by P1. P1 we already know. P1 was given the question 98 kilopascal, right? 98 kilopascal. So it will be 98 kilopascal, 98. So it will be approximately 4.758 kilopascal. Similarly, we can find QV2, that is 0.622 into ES2 by P2. It is 0.622 into ES2 is 2.339 divided by P2. P2 is nothing but P2 we have calculated, and it is coming out 77.95, 77.95, which will be approximately around 0.01866 kg per kg. So we got QV1 and QV2. So QV bar will be equal to QV1 plus QV2 by 2, that is equal to 4.758. No, sorry, there is a mistake. So here QV1 will be equal to, if you apply this particular formula, QV1 is equal to 0.0302 kg per kg. Okay. So the average value will be 0.0302 plus 0.01866 by 2, and it will be coming around how much? 0. I'll be sharing this particular PDF with you, and you can work this out. Okay, so we got all the terms now. So we directly can find the incremental precipitable water that is there in the first 2 kilometer column. So we have the average density of air in that particular stretch, that is equal to 1.0025 1.0225 into the average specific humidity is 0.02443, and delta Z is nothing but 2 kilometer. So if you solve this, we will be getting 49.96 kilogram. So that this much volume, this much mass of precipitable water is there in that particular 2 kilometer of water column. Okay, so such questions, what we need to do, we need to be knowing these relation. One relation is this thing, that is the gas flow relation, then the lapse rate, how temperature varies, then what we need to remember is the pressure relation, that is pressure, how it is related to temperature. If pressure is related to temperature, you know the temperature will reduce, then the pressure will also reduce. And once that is clear, then we have a relation of specific humidity with vapor pressures. And one more relation that we have to remember is the relation of the saturated vapor pressure with the temperature. Okay, so I'm stopping here. So I think we have almost covered most of the uh, important concept that ma'am has covered in the previous week lecture. So if you have any doubt, or if you have any doubt in the assignment questions also, you can contact me through mail. So my name is Akhil G. My email ID you can note down. So if you have any doubt, you can contact me through this mail. Okay, then thanks for joining. So we can see in the next week. Uh, do you have any doubt, Pavitra? Like, otherwise I'm stopping here. Hello. Yeah. You can contact. Yeah. Yeah, mail. Yeah, fine. It's so I have not gone through the assignment. I have had a glance of it, and but wherever you're having doubt, you can just let me know. And if you, I will be sharing this particular material also. So where if you have any doubt, because today is the time I have exceeded, so I had to rush in the end. So if you have doubt anyway, you can contact me for this thing also. Okay, then thank you. Thanks for joining.